The final slidecast in this chapter looks at applications for maps. Now, if we look back to the phone directory problem that we did at the beginning of the course, the problem is to use a map to obtain a more efficient implementation that's better than order n for our phone directory. Originally, we used an array and then a vector to implement the phone directory. Now, a map will associate the name with a list of phone numbers. So here we have names, which are unique values that will serve as keys or our index into our map, and then here are the phone number values associated with those names. So we could implement the phone directory ADT by using a map which will have a string key associated with a string value. And this map object will contain key value pairs, and here's some examples. So in our design, here's our API to do the operations, to add or change entries, to look them up, remove them, to load our phone numbers originally, and to save it to disk. So that was our phone directory API, and here's kind of the underlying map API that we can use in terms of delegation. To add or change an entry, we can use the indexing operator on a map to access that entry. We can use find and erase, and we don't have a map API to support load data and save data directly. So for implementation to add or change a directory, this function is slightly inefficient since we do two searches of the map. So if we want to add a given name with associated phone number, first we look up that name in the directory, and it'll return their old number. And then we can reassign the new number, set modified to be true, and we'll return the old number. So the point here is, we do two lookups in our directory in order to implement this. Now here's a revised version, add or change number. We first set old number to be the empty string, and then we can insert into the directory a pair, the pair that associates the name with the new number. And by calling insert, the result of that will be a pair that's an iterator and a Boolean result. That'll be either set to true if we're adding this name for the first time, or else it'll have an iterator that points to the existing phone number if that person already exists in the directory. And if that person is already in the directory, then we'll use the iterator to grab the old number and to reset, change that phone number to the new number. And then we can return this. So here we only do one lookup into our table, or into the map. Here's an implementation to look up an entry. The lookup entry, we first call the find function to get an iterator, and if the iterator is not equal to the end, then we have the name exists and we'll return the phone number. The phone number will be the second item in the pair. Here's remove entry. Again, we'll do a lookup for a person's name to get the old number, and then we'll erase the entry associated with that name. And modified, if the old number is not equal to the default string value, then that means that there was a number for that name, and modified will be true. Here's an implementation for load data. It reads entries from a file and stores them in the map. So we can use a while loop. As long as we keep getting in names and numbers, then we will use the indexing operator to take a number and assign it to the entry in the directory associated with the key. Now to save the directory, we need to extract each name number pair and write them out. And here's a for loop to do that, again using iterators. And to test this code, we could modify our original CPP file to use map-based pd.h. We compile and link the modified source file with map-based pd.cpp, and the rest of the main function used to test the application will be the same. So this is a nice example of how when we use our abstraction for certain data types, we can come along with a more efficient data type, and if we've done with sufficient data hiding, it's not complicated to replace an inefficient data type with a more efficient one. Now, Huffman coding, the problem is to build an array of weight symbol pairs where the weight is the frequency of occurrence of each symbol for any data file. And we can encode each symbol in the input file by writing the corresponding bit string for that symbol to the output file. So for each task in the problem, we need to look up a symbol in the table, and using a map ensures that the lookup is expected to be order log n. Now, for our analysis, for the frequency table, we need to read a file and count the number of occurrences of each symbol, and the symbol will be the key, and the value will be the number of occurrences. And as each symbol is read, we retrieve its map entry and we increment this corresponding count. And if the symbol is not yet in the frequency table, the map subscript operator will insert a 0 the first time we reference it. Now, once we have the frequency table, then we can construct the Huffman tree using a priority queue, as we talked about back in chapter 8.6. And then we build a code table that stores the bit string code associated with each symbol to facilitate encoding the data file. And then we store a code table in a map that for each character we associate the Huffman code bit string. That's that string of zeros and ones. And the object makes the encoding process more efficient because we can look up the symbol and retrieve its bit string code in order log. It's an order log n process. So to build the code table, we do a pre-order traversal of the Huffman tree. So the algorithm to build the frequency table, we read the input file, and we increment the entry in the map associated with the character. For every entry, we store its data as a weight symbol pair in a vector of Huff data, and then we return that vector. Once we have the frequency table, then we build the codes. We get the data at the current root, and if we've reached a leaf node, we insert the symbol and bit string code so far as the new code table entry. Otherwise, we append a 0 to the bit string code so far and apply the function recursively to the left subtree, append a 1 to the bit string code, and apply the function recursively to the right subtree. Now, the algorithm for the encode function is while there are more characters in the input file, we read a character and we get its corresponding bit string code, and then we write its bit string code to the output file. So here's the code to do the build frequency table, which is reading characters and then updating the map. And to test this, we can download class bitstring and write a main method that calls the methods in the proper sequence. We could read a data file and display the frequency data. We can use the string class instead of bitstring in the functions build code and encode to build a code of characters 0 and 1 instead of bits to verify its correctness. It's just for display purposes and so that we as a human can verify it. And that brings us to the end of this slidecast.